the takeaway from this webinar should be the understanding of computer-aided drug designing. What is computer-aided drug designing? The audience should get the understanding about this, and why the CAD is the need of the hour. Apart from that, what are the advantages of CAD? Before the advent of computer-aided drug designing, what were the lacuna, what were the gaps which CAD has very successfully filled up? And what are its state of the art and tools? What are the procedures? And last but not the least, is CAD really successful? We will have all the takeaways from this webinar. Let's cover up one by one. To understand the importance of CAD, we must first get the idea of traditional drug discovery approaches. The first overview of this is like, there are medicinal chemists, there are pharmacognosers, they do search, they do explore novel compounds. But in traditional ways, what was going on? Suppose if I am a medicinal chemist, which I am. So what we used to do in previous time, we used to synthesize, because anyhow, if I have a M.Pharm and I have PhD in PhD work, and I had designed some scheme, and I will continue my life around that scheme. I don't want to explore any other things. I just know how to prepare. Let's say, for example, I know how to prepare quinazolines. People used to prepare all their life around quinazolines, different derivatives. And they were, let me tell you, they were, and most of them are till today, they are designing it blindly. They are designing it blindly. Let me tell you more precisely, they were designing it very blindly. They had no scientific rationale, like, why should this be? They had just some blind rationals, blind guess that it should be active, but there was no rationale behind being the activity of that compound which they were synthesizing. In the same way, for natural product chemists, they used to synthesize they used to extract molecules from the plants, and they had no idea whether actually this would be active or not. They had no rationale. So this is one. And of this, this is time consuming part of that drug discovery. It involves money, it involves human personals, it involves chemicals, it involves time, it involves cost. And most important thing, what to me is, if we are synthesizing blindly, if we are exploring blindly, we are wasting our resources. We are wasting chemicals, and those chemicals which are going into the environment, they are spoiling, destroying our environment. That is one of the most thing which hurts to me. So after this process, the next step comes preclinical trials. The preclinical trial is activities, carrying out different pharmacological, biological activities, microbial activities. Then comes clinical trials in human. Preclinical is whatever you are doing, identifying toxicity, identifying its activity, all those comes under the umbrella of preclinical trials. Then when this is safe and this is effective, then scientists move on to clinical trials, to human trials. into humans. And when the four clinical stages are successful, it becomes a drug, an approved drug. There are all other processes for approval, that is different topic. But into this process, these steps are very time consuming and expensive as well. And the result is very low. The success rate is very low. Now let me compare it with the rational or modern drug discovery approaches. The modern drug discovery approach starts from, it just doesn't start from synthesizing or exploring natural products. It starts from target identification. It starts from identifying the disease, identifying the pathophysiology behind it, identifying the stages, and then which enzyme you need to block. Yani, you need to identify your target. Target can be any enzyme, it can be any protein, receptor, all those things. By the way, receptors, enzymes, they all are proteins. So here first, you have to identify the mechanism of disease and then the target. Once target is identified, then we need to identify the lead. We need to identify what chemical compounds, what new chemical compounds or existing chemical compounds can inhibit this target. This is lead identification. This can be through chemical synthesis. This can be through screening existing natural compounds, or through Me Too drugs or repurposing. Nowadays, there is a lot of talk around repurposing of the drugs for existing drugs, of course. Once that lead is identified, then we optimize the lead. We make some changes and again go back to the inhibition of the target. Once all these things are happening in silico, inside the computers, when your lead is optimized in various ways, you have you can optimize it being an oral drug, you can optimize it by activity, you can optimize it by the least toxicity having. So when you are optimizing it, after that you synthesize it and go to the real with real in vitro or in vivo studies. Then comes preclinical trials, and the process is like the traditional discovery processes. But here, all these steps, they come under the umbrella of CAD. The advantages are it's time and cost saving. When you are saving your time and cost, you are saving environment as well. You are not unnecessarily synthesizing a lot of hell of compounds, million of compounds, and wasting alcohol, wasting all the chemicals. So this is one thing. And the success rate is very high. I will show you some data, and you guys will be amazed how successful CAD is. And actually, still now, people are not realizing the worth of the CAD. So when all this here is consuming, is cost saving and time saving, the success rate of achieving a drug is quite high. I'm not saying very high, but is quite high in comparison to the traditional drug discovery approaches. Now let's see what types of CAD are. CAD is basically classified into two parts. One is structure-based drug discovery. One is ligand-based drug discovery. Structure-based drug discovery is applied when you know about the structure, when you have some knowledge about the structure, which is further can be a known structure, or it can be divided into unknown structure. There are two approaches. For the known structure, you have already the structure. You can, most of you guys may be knowing it. The known structures can be found on PDB websites. There are few websites like RCSB. These are basically protein data banks where the proteins are saved for various types of receptors, enzymes, all the targets. So in structure-based drug design, when that structure through PDB, we can download it and then process it, repair it, and then you can further carry on your CAD steps on that. The next type is when there is unknown structure, when the structure is not well known. Actually, what happens, maybe we do not have exact structure for some, maybe for some bacteria or something, but we have some related structures. We consider it as template, the related structure, and on that template we build up our protein. That is called homology modeling. And if we model that protein, and which is homolog of other types. So in SBDD, we will go in more details, but to have an overview, SBDD is one when there is a known structure, and other when you are preparing the structure, when you are preparing the protein. The next type is LBDD. LBDD stands for ligand-based drug discovery approaches. In the ligand-based drug discovery approaches, there are two types. One is QSAR-based approach. Another one is shape screening. Can I request, guys, please do not draw anything on the screen. Please take care. I know there are grown-up guys. Okay. So in the ligand-based drug discovery approaches, there are two types of approach. One is QSAR based, and another one is shape screening based. Shape screening based, you can call it pharmacophore mapping also, pharmacophore studies as well. So let's see QSAR first. Let me tell you about QSAR. Many people are not well aware about QSAR. The definitions in the books are not very very clear to make the people understand about QSAR. Let me start from SAR. Being from the pharma background, everybody knows what is SAR, structure activity relationship. We are teaching the students, we are learning by for our own self. The people who are writing are really giving hard time. Anyway, QSAR. Actually, I was talking that everybody knows SAR. In the books, in the literature, it has been written that if there is a basic pharmacophore, and if you are adding this electronegative group, it can improve the activity or it can decrease the activity. That's what we are learning in SAR, right? But in SAR, we are telling that this electronegative group or this electron withdrawing group on some position can increase or decrease the activity. But how much it increases or it decreases the activity, there is no data about that. Nobody was talking in last decade about that. So when we quantify the effect of that electron withdrawing substituent or electron donating substituent on the activity, when we quantify it, that is called QSAR. You are quantifying it, how much effect it will give, this substituent will give. That is defined as QSAR. This is up to the definition. Then comes, how do we carry out QSAR studies? How do we, what are the procedures applied into the study? So let me tell you. See, you can go through to get an overview about QSAR. You can go through this part, like QSAR and drug design. For that, QSAR, as I told you, this is part of LBDD, ligand-based drug designing. we have already many drugs, but we want to improve it. Yani, we have some compounds and their biological activity. We have some known data. And with this data, we make some QSAR models, and then we predict for new compounds having improved biological activity. How all this happens? So let's see here. Like we have a reported leads, as I told you here. For this leads, we have biological activity as well. Now, what we do, we calculate different descriptors for this reported lead or number of leads. We can there are thousands of descriptors. One of the free website is eDragon. You guys can Google it and find it. From the eDragon, you can calculate number of descriptors, and for each molecule, actually these descriptors are calculated for each molecule. Whatever you have, for example, you have 10 molecules, you have 100 molecules, molecules of series. For example, my area is, let's say, quinazoline. Maybe from the literature, I will get hundreds of quinazoline molecules with their biological activity. And for these 100 of molecules, I can calculate 10,000 descriptors. And then we developed a statistical relationship between this descriptor and the biological activity. That statistical relationship is called QSAR or 3D QSAR. What is the difference in QSAR and 3D QSAR? If you are among the descriptors, if you are calculating steric descriptors, you are counting on steric descriptors as well along with electronic descriptors, then that is 3D QSAR. But if there is no accountability of spatial arrangements, that's only QSAR. So there can be hundreds of descriptors can calculate with while using different softwares. So biological activity, descriptors, and then statistical relationship. Okay. That creates QSAR model. With these models, of course, there are certain points for a model to be successful. There are some values. You have to prepare a successful model, and from that model, you can prepare new series. You can predict the activity of any molecule you design, and you can predict its activity based on that statistical model, and that gives you the leads. So this is a short summary of QSAR. Then comes structure-based, just a second. Just a second, please. I don't know how to hide these, but there are protein structure. I was talking about SBDD. In SBDD, we are working around the structure of the protein. That protein, either you prepare it through homology modeling or you get it through PDB, or I mean, you have already reported protein. Now, in structure-based drug design, that protein, when you download, you have to identify the binding site. What are the binding pockets, or what are the active domain of that pocket? Through binding site identification. There can be a software like QSite. There is a software which identifies the active pockets inside the protein. So the first step is identifying the binding site, number one. Number two, if somebody doesn't have that software, or your design can be like, you can go inside, you have downloaded that protein, and there must be a ligand. If there is a ligand, an active ligand already reported, you can extract that active ligand from the active pocket, and you have identified that active pocket. Here you can dock your own molecule, because that binding site is already identified. This molecule was downloaded and it has a ligand, an active ligand. You are extracting it out and trying to fit your molecule inside. So that is called docking. Docking is basically fitting of your molecule inside the active pocket, inside the active domain of any receptor. So when there is a new molecule, it can be docked over here. Or when you have binding site identification, you know how binding site is there, what kind of residues are present inside the active domain. So here you can design, or a scientist can design a new molecule based on the insight of the active domains. What sort of residues are there that they will prefer to bind with? Suppose this is the shape. You need to prepare a complementary molecule which can fit over there exactly. So this is de novo designing. You can design a molecule which fulfills the requirement of an active pocket to bind with. This is one approach. Now comes the docking. In the docking, not only small molecules can be docked, but not only small molecules can be a drug, but protein itself can be a drug. There are various proteins. So these protein can be docked into that protein as well. Of course, small protein can be docked into this big receptor as well. So there are two types of docking: ligand protein docking and protein docking. This was all a short introduction about structure-based drug designing. And there are number of softwares. The top citing software is Autodoc. Autodoc is one of the top cited software, and this is free. So a lot of people are doing nowadays molecular modeling studies with the help of Autodoc. And nowadays there are n number of softwares available. Even some are web-based softwares. You do not need to download it. You can upload your molecule. You can upload your protein, and the process can be done on the server of the host. Now let's talk about the success stories. This is for those people who do not realize the worth of CAD. There are many drugs, many reported drugs, which paved their way of success while using CAD. Some examples are amprenavir, nalfinavir. As you can see, there are n number of drugs. They were designed by targeting their proteins, their receptors. So this is the success stories, and there are n number of drugs. These are few examples which are well-known drugs, but there are many examples nowadays. I was talking about success rate of CAD. As I told you in the previous slides, that the success rate is very high with CAD in comparison to the traditional drug discovery approaches. Like you can see, in traditional high throughput screening, 400,000 compounds were tested, and 85 were featuring inhibition, producing a hit rate of only 0.021%. And there is virtual screening using CAD, computer-aided drug design. So the database was 235,000 for commercially available compounds, and that yielded 365 compounds, 127 of which showed effective inhibition, a hit rate of nearly 35%. So you can compare the hit rate. It is awesome. It is quite successful. The disadvantage, you can say, is there sometimes we get pseudo result as well, but there can be n number of reasons for that. So hit rate is quite significant. We cannot negate the role of computer aided drug designing. We cannot deny from it nowadays. CAD and COVID. Role of CAD in the research of COVID-19. Like, for example, today I was just going through PubMed, and when I typed COVID-19 and docking, see, the number of results are 201. You know, let me tell you, apart from this, being the research for COVID-19 is not very easy. You cannot directly, because testing against this virus is not easy. We need a very a biosafety lab, completely biosafety lab, and which is not easy to be established by any institution. Only top-notch research organizations can establish that lab. But here comes the significance, here comes the opportunity for CAD. We as a medicinal chemist, we as a pharmacologist, having research background in pharmacy, we can utilize this CAD, and we can see the number of research is 201 for docking. In the same way, when I researched COVID-19 in silico, the result was 240, which is nothing. There is still a lot of scope for molecular modeling studies into this, because when you will type only COVID-19 into PubMed, it will give more than 30,000 results. More than 30,000 articles have been wrote on COVID-19. But see, in silico is not that much. Still, there is a lot of scope for computer-aided drug designing into the COVID research for their role. So COVID is giving opportunity, CAD is giving opportunity for the research in overcoming COVID as well. So there is no question that